Hey folks, so I wanted to talk just a little bit about these very scary looking graphs that we call solubility curves. They look really overwhelming, mostly because you just have a very large number of curves all on one graph, and it's kind of a to try to kind of figure out what they all mean. They're actually really straightforward to read, though. Why do we put everything all on one graph? Well, it kind of allows us to compare two things. So if I wanted to compare lead nitrate and potassium nitrate, I can see a couple of things. First of all, that lead nitrate has a much more steady incline, so that if I want something that's going to dissolve more steadily, lead nitrate's going to do that. Whereas potassium nitrate starts off a little slow and then it has a really steep up kick in its curve. So it's got a real sweet spot in its temperature. Okay? We can also use it to compare when is their solubility the same, so where they cross. All right? So these graphs, we use them a lot for all sorts of different things, and they look very, very messy, but they're actually not too bad if you know a few very simple things. So first of all, I would say the first thing you should always, 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 always do is look at the axes. Okay, first of all, the x-axis is in temperature, okay? Because one of the major components that affects solubility is temperature. We all know, because we all make sweet tea, because we all live in Texas, and that's what we do here. We all know that sugar will dissolve better in hot tea versus cold tea. All right, but let's be a little more specific, okay? We can say that with a solid, all the curves are going up. But there is one curve that goes down. See it? Why would a curve go down? Well, really important concept here that we keep these straight. If the curve goes up, your solute is a solid. Okay? Let me explain that for a minute. Why does increasing the temperature make a solid dissolve better? Why is more solid going to dissolve at a higher temperature? Well, it's about the state of matter. Solids are very, very dense. Their particles are tightly packed together. They have a tendency to want to go down. They want to sink. They are generally more dense than liquids. Not always, but usually. And so when we're talking about dissolving it, how do we keep it from sinking to the bottom? Well, water molecules are constantly moving. Now, the speed at which they move is dependent on their temperature. The higher the temperature of the solvent, the faster those water molecules are moving. So I like to imagine the solubility of a solid like a juggler. The faster those water molecules move, the more they're able to keep those solid particles from getting to the bottom. They're able to hold them up and afloat. Okay? And so when things are at a much colder temperature, the water molecules aren't moving very fast. The solid is able to sink because there's nothing to catch it, because the water molecules are moving too slow to catch it. We heat that up, the water molecules are moving more quickly, you're going to be able to keep those solid particles more within the water. The opposite is true if our solute is no longer a solid, but a gas. If your curve goes down, like that Ce2SO43, that means your solute is a gas. Let me explain. Gases are the opposite in terms of what they're trying to do. Solids are trying to sink. Gases are less dense. Their particles are far away. They want to float to the surface and escape. Okay? The slower my water molecules are moving, the more in the way they are. And so they're going to be able to keep that gas in just because they're in the way. But if we speed those water molecules up, suddenly our gas particles are able to sneak past them and escape. That's why when they bottle soda, they add air on top. That's why when you open a soda, you get that psh. They've added extra air so that it's pushing down on the surface of the liquid so that it keeps that dissolved gas in. Because instead of just the water molecules holding it down, they're also adding extra air to hold it down. The water can hold it down because you know that when you first open a soda, it doesn't immediately go flat. It takes a while for it to go flat. And the reason it takes a while for it to go flat is because the gas particles have to somehow get past the water molecules that are holding them in. But if the soda is, let's say I left the soda outside in the sun versus in the refrigerator, okay, after I've opened it. The soda that sits out in the sun is going to have the gas escape way more quickly because the gas is going to expand in the heat and it's going to be able to rise more quickly. The water molecules are moving really, really fast, so they're going to get out of the way. That gas is going to escape, okay? Whereas if it's in the fridge, my gas is staying a lot more compact because remember, a cooler gas is a smaller gas. Okay, so my gas particles are staying more compact, but the water molecules are also moving more slowly, so those gas particles can't escape as easily past them. Okay, so really big idea there, guys, is what direction the curve is going. If it's going up, you're talking about a solid, which most of these are solids. Most of them are going up. We have only one that is going down, and that's the Ce2SO43, and that means that it's a gas. So first thing you want to do, look at that axis, figure out what you're looking at. These are all solids, this one's a gas. The second axis we want to look at is this one right here, the y-axis. This is telling me about the solvent, what I am dissolving this in. And the really important thing here is how much we have. How much water am I putting this in? One thing that Edgenuity doesn't mention to you that you might find handy is that 1 gram is the same as 1 milliliter. So we can use 100 grams of water or 100 milliliters of water interchangeably because it's the same amount. They do that in Edgenuity and they don't really explain why. Why? Because they're equal. This is tricky because this solubility curve graph only represents the solubility of these different solutes in 100 grams of water. Well, we may not always be working in 100 grams of water, but that doesn't mean that this information isn't useful. All right, but you do need to be aware of how to adjust for that if it is different. And we'll do a couple of examples of that in a little bit. But first of all, always make sure you know what your axes are talking about, because that's going to be really important. The second step is to find the curve you want. As we say, there are a lot of curves on this graph. And really, we're usually going to isolate 1 or 2 to look at any given time. Where do these two have the same solubility? Wherever they cross. But one thing that we'd like to ask you to do is to identify whether a solution would be unsaturated, saturated, or supersaturated. So we would give you a temperature and a amount of solute, and we would ask you, what kind of solution is that? Saturated, supersaturated, or unsaturated? So let's talk about how to know the difference. Let's start with unsaturated. An unsaturated solution is one where more solute can be added and it will dissolve. Okay? Let's look at the K2CR207 curve. That's this purple one right here. Let's look at that guy. I'm gonna erase what I just drew so we can actually see the curve, but I wanted you to see which one I'm talking about. Let's look at that curve real quick. If I said that I had 30 grams at 80 degrees Celsius, that would be, here's 80 degrees Celsius, I'm going to follow that up, oops, to the 30 grams. Okay? This is below the curve. So everybody see that? My curve is way up here. I ended up below the curve. Okay? That is an unsaturated solution. What that means is, so if I could still add more solute, I'm not all the way to that curve, that is an unsaturated solution. All right, let's look at a saturated solution. Saturation is the maximum solubility. This is the most solute the solvent can hold at that temperature. This is always determined experimentally, and this is where those curves came from. So somebody went to their lab, took some K2Cr2O7, and they started it at 0 degrees Celsius, and they looked at how much would dissolve, and they recorded that amount. Then they warmed it up to 20 degrees Celsius, and they kept adding more of their solute until they figured out how much would dissolve. And they keep doing that at various intervals until they see what the curve is going to look like. That's where the curve came from. So if your measurement hits on the curve, exactly perfectly on the curve, that is a saturated solution. That's a sweet spot. That is where we have exactly as much solute as that solvent can hold at that temperature. But now this last one, I love this last one because it's so easy to teach in Texas because we've all done this. The last one is called a supersaturated solution. It's a tricky idea, but not here in Texas because we do it all the time. Supersaturated is where we heat the solvent to add excess solute and then gently cool. Now, if you've ever gone to a restaurant and they accidentally brought you an unsweet tea because they forgot they were in Texas and they didn't know what they were doing, and you tried to add sugar to it, that iced tea full of ice, it's not going to dissolve a lot of sugar. You are not going to get anywhere close to what we would consider Texas sweet tea by trying to add sugar to your iced tea. Okay? Because the solubility at that really cold temperature is very low. So when we go to make our Texas sweet tea, we always start with hot tea. We add a bunch of sugar to it, and then we very gently cool it back down so that the sugar stays suspended even though it is no longer, even though we are past our saturation point. So that's a supersaturated solution. Now, those can be really fun because you can take just a single crystal of sugar or whatever your solute is, or scrape the bottom of the container, and all of a sudden it'll crystallize. All of the solute falls out of solution all at once in a big giant crystal. This is how they make rock candy. There's some really cool demos online. I'll try to find some links to put in Canvas for you of some demos of taking a supersaturated solution and pouring it out, and it goes from being a liquid to being a solid because it crystallizes because of the jarring action. It forces all of those crystals to fall out of solution all at once. So supersaturated solutions are very, very cool. Very fun solutions to play with. All right, so some scary, scary problems that they give us. I felt like Edgenuity did a pretty good job of explaining some real basic questions about just kind of reading the graph. Temperatures on the x, solubility is on the y. So you follow the x and the y axis to your point, and you decide, is it, oh, I'm sorry, I didn't tell you. Supersaturated is when we're above the curve. So if we end up above the curve, we're talking about a supersaturated solution. So there are a few questions that Edgenuity is going to ask you where it's a little tricky. And so let's look at a few questions that I think are going to try to trick you up. All right, so let's say if 35 grams of KClO3 is dissolved in 200 grams of water at 70 degrees Celsius. What type of solution is this? Now, if you're not paying attention, it would be very easy to call this a supersaturated solution. But if you do that, you're going to get it wrong. Because if all you look at is the 35 grams and the 70 degrees, well, 35 grams would be here, 70 degrees would be here, so we're above the curve, right? So that's supersaturated, except for one thing, 200 grams of water. 200 grams of water. This graph is in 100 grams of water. That's twice as much water. So we're saying that we have 35 grams in 200 grams of water, but our graph is in 100 grams of water. So we need to make this equivalent. Now this is fairly straightforward because it's just half as much. So we have half as much water, so it's half of 35. Let's call it 18 grams. So really, we would have 18 grams at 70, which would be down here. That would actually be an unsaturated solution. So if you're not careful and you don't watch this y-axis and make sure that you're matching it, you can get this very, very, very wrong. All right, so let's try another one like that. Okay, so if 15 grams of KNO3 is dissolved in 50 grams of water at 5 degrees Celsius, what type of solution is this? Now again, if we're not paying attention, we see 15 grams at 5. Well, 15 grams at 5, that's like right on the curve. That's saturated, right? Wrong. Because it's not in 100 grams of water, it's in 50 grams of water. So we have 15 grams in 50, that's not 50, sorry. We have 15 grams in 50 grams of water, but our graph is in 100 grams of water. So how much are we really talking about? Well, this is twice as much water, so we're really talking about twice as much solute. So that would actually be 30 grams. So what type of solution is this? Well, let's find out. So if we have 30 grams, that's way up here at 5 degrees Celsius. That's going to be a supersaturated solution because we're above the curve. considerably above the curve. Curve's way down here. Okay, so really watch for this. If they tell you how much water, make sure you're checking that with the graph. Make sure that matches, okay? If it doesn't match, make sure you adjust it accordingly so that you're in the right spot. Hope that helps, guys.